Hello everyone, this is Kaveh from Hawaii. I don't know if you can hear it, but there's some bird singing in the background today, which is nice. Okay, so we're on lesson 5, Common Lisp and OpenGL, and I think we'll have a little bit of a briefer lesson today. We'll see how it goes. So the first thing I'm going to do is I've been trying to have a way that you can basically run these lessons yourselves and just evaluate the files and run the code and so on. And I'm finding it difficult to maintain that consistency because I put a lot of test cases and expressions to evaluate in the files. Sometimes in deliberately redefining things, introducing errors so you can recover from errors and so on. So I'm going to remove this part from the files from now on, and I'm going to trust that if anybody is following along, they'll be aware and have the wherewithal to know what to do. So we'll see how that goes. Um, so first I wanted to talk a little bit about one aspect of Lisp, and people talk about Lisp not having types, Common Lisp. Common Lisp does have types. The difference with other languages, is that in Common Lisp, variables don't have types, values have types. So the type of a variable is determined by what it's bound to. So for example, if I define my parameter for var, and then I get a type of var, it's a single float. But what I can then do is I can assign a string to var, and nothing prevents me from doing that in Common Lisp. Because var doesn't have a type, var is just a placeholder, and you put in values, and the values have types. So if I then look at the type of var now, it's a string of length 6 in this case. So this is very useful when you want to, first off, create heterogeneous collections. For example, if you have a list that has numbers and strings in it, you can do it very easily. In a lot of other languages, it's almost impossible. You have to define a type of the list, type of the contents of the list, and so on. And if you want to put a string and a number in there, you have to make classes for them and then make sure they're subclasses of the same parent class, and then make a list with that parent class as the item type. And it's just a nightmare. But so Lisp does have types. Every value has a type. In that sense, it is strongly typed. But you're free to basically assign any value to any variable that you want to, which is very, very useful, and especially if you're doing rapid prototyping and so on. One of the things I find nice about Lisp is that you can sit down and just start writing your code without having to go through a lot of boilerplate and define all kinds of stuff that you don't need to worry about at this point. If you do need to worry about types for efficiency purposes in Lisp, you can then have declarations later. But my philosophy is you never try to optimize without profiling first. There's a saying in programming that optimization is the root of all evil. Or excuse me, premature optimization is the root of all evil. And people try to design their systems to be very optimal from the base go, and run into problems because the system becomes inflexible as they do their development. All right, let's move on with today's lessons, which is about groups. Groups are a lot of fun. They let us create hierarchies, and hierarchies are essential for computer graphics, especially for animation purposes, where you want objects to be parts of other objects. So if I have a car and it's got 4 wheels, I want to group those together so when I move the car, the wheels move with the car. But the wheels, being children of the car, also have their own transforms, and they can move independently of the car, so they can rotate as the car moves, and so on. And car doors can open on their own, but they can be part of the car, so the whole thing moves together. And hierarchies can be nested arbitrarily deep because you have things that are part of things that are part of things. If you imagine something like the Transformers robots from those movies, they probably have tens, if not 100,000 parts that are all grouped together in a hierarchy, and they all move and animate together in relation to each other. All right. So a utility for printing spaces, we'll find out why we need that a little bit later. But we're going to define a new class, subclass of shape. So it's going to have a transform, but it's a group. And it has a list of children, which starts off as always as the empty list. So our group is basically going to contain shapes, and then when we transform the group, or move the group, or rotate the group, all the shapes rotate and move with it accordingly. So we define a utility function to add a child to our group, so we can add a shape to our group. And then to draw the group itself has no geometric content, basically. It's just a placeholder that holds children. So we do our map C, which traverses a list, and calls the draw function on each of the children of the self. And since we had the before and after draw methods earlier, the matrices get pushed and popped accordingly, so that everything is taken care of. We make a convenience function called makeGroup that basically just makes an instance of group. Let me prevent my phone from beeping during this session. There we go, silent mode. And then we can print out a hierarchy with some indentation so we can actually see our groups listed. So the print hierarchy, we define it on scene to start with, which is our top level container for all our objects that get rendered. And it prints some spaces, so it has an indentation. That's why we have the print spaces function we defined earlier. It prints itself out into the standard I/O, terminal I/O, which is T. And then for each of the shapes that are in the scene, it recursively prints the hierarchy for the shape with an indent that's 2 greater. So all the children will be indented by 2 from the parent. And then if we have a print hierarchy for our shapes, it just basically prints the spaces and then just prints out the shape itself, and that's all it does. And then again, we use an after method for print hierarchy on groups, so that once the group has printed itself, because group is a subclass of shape, the after method gets called, and it basically goes through all of the children and prints a hierarchy for the children with an indent of +2. And one little improvement that we do to print objects is if we just print a polygon shape, it just gives us an address and says polygon shape of that thing, so we have no idea what it is. So one of the things we'll do to help ourselves is in the string of the polygon shape, we'll print how many points it has, so we can have some idea of which shape is which in our particular case. Obviously, if you're doing more serious work, you need better ways of identifying your polygons and your shapes. So we just take the length of the points of self. So let me just go back and evaluate these one by one. So just compiling these as we go along. Actually, let me just select all these and evaluate the region. So all that has been evaluated. Now, let's create 3 shapes. So we've created 3 shapes: hexagon, square, and triangle. And these are just global variables. We haven't put them in the scene yet, so nothing is showing up in our scene window. And let's make a group called group 1 of the square and the triangle, and then print the hierarchy for it. So here we have it. So this is group 1. And then it has 2 shapes, 2 polygon shapes as children. And we can see that which one is the square, which one is the triangle, because we're printing a number of points. So you know this is the square and this is the triangle, and they're both children of group 1. Now, if we make a group 2 that contains group 1 and the hexagon, then let's evaluate that and print that. and see what that looks like. So this is, you have to kind of know that since group 2 is a top level group, group 2 contains group 1 and contains the hexagon, which has got 6 points. And then group 1 contains the square and the triangle. So it's not the most obvious thing, but it's enough for our diagnostic purposes to understand what the structure of our groups is. And now we can add group 2 to our scene. So you can see that basically we have a square, a hexagon, and a triangle just all in the scene. And they're all sitting at the origin because they have no transforms or anything. Now, to better understand how the transforms work in groups, let's add a slot to our shape class. We're going to add a Boolean slot called show axis. Again, I use a question mark as a idiom to indicate that it should take a Boolean value. And show axis basically decides whether or not the shape, when it gets drawn, draws an axis for itself, so we can see where its center is and where its axes are. So we override or redefine the draw after method for shape. If you remember from the previous lessons, before it would just pop the matrix for OpenGL. So here, before it pops the matrix, it just checks to see if it needs to show the axis. If it's true, if so, it just calls draw axis on itself, still in the current matrix stack state of the shape, so that it moves with the shape. And once it's done, it pops the matrix. And draw axis is pretty straightforward. Again, it just like draws a pair of lines. We assign colors to them, so we assign a red line that gets drawn at the origin of the shape and plus 0.25 in x, so that's basically the x-axis of the shape, and that's going to be red. And then I made it a slightly off red just to be artistic, so it's not a pure blaring red. And then a green line for the y-axis, the same way. And before we start playing with the axes, I have another function that I wrote. Is basically, now that we have hierarchies, it's useful if we can execute things on an entire hierarchy all at once. So we can traverse the hierarchy and execute a function on every node in the hierarchy. So the way we do that is basically define a function called doHierarchy, takes a shape and a function, and for the case of a shape, it just function calls the function on the shape, and that's all it does. And then there's an after method for groups, just like the print after method, that once it's been called on the group because it's a class of shape and the function's been called on the group itself, it loops through all the children and calls recursively doHierarchy on each child. And then if those children are groups, of course, then recursion continues and we go down the tree. So let me evaluate these. Compile, compile, compile. All right. So what I'm going to do now is I'm going to do a doHierarchy on group 2, which is our top group, and tell it to set the show axis of every node to be true. So you see in our window that we have a red x-axis and a green y-axis. And since all the shapes are superimposed at the origin with no transformations, all the axes are overlapped, so we only see one axis. But now, let's take our triangle shape and move it in y. So I keep executing this expression, and you can see that the triangle's moved in y, and you can see its axes up here. So this is now the coordinate system of the triangle. And if I rotate the triangle here by 10 degrees, you can see that it rotates, and the axes rotate with it. Now let's do the same thing with the square. Let's move it down in y and negative y. So it's moved down in y, it's got its own axes. Now, if you remember, the square and the triangle are in a group called group 1. So if I take group 1 and I move group 1 in X, we can see that they move together, and this is the axis and the center of group 1. Even though group 1 has no geometry, it still has axes, an axis and a coordinate system because it has a matrix, a transform. So this is where group 1 is now located. This is the position of group 1. And the square and the triangle are relative to group 1. So anytime group 1 moves, they move with it. And if I rotate group 1, you can see that its children, the square and the triangle, rotate with it. Now, if I rotate group 2, which is the parent of everything, you can see that everything rotates. If I scale it down a little bit, everything scales down. And then if I translate group 1 again in X, it moves along the axis of group 2, which is the parent. And then if I move group 2, you can see that everything moves. So this is the fundamentals of groups and hierarchies. Time for some coffee. I hope I'm not getting a milk mustache as I do this talk, but I can't see myself while I'm doing it, so we'll find out later. And if I do, I'm too lazy to redo it, so it'll be fine. It'll be part of my branding, the milk mustache common Lisp listens. All right, now what we're going to do is we're going to take a new shape, a pentagon, and we're going to add it to group 1. So the shape will appear where the origin of group 1 is, which is where the axes are. So you can see that the shape appears here, and it's at the location and at the rotation of group 1 because we made it a child of group 1, so it automatically inherits those transforms. Now, if I take the same pentagon shape and I add it to group 2 as well, then you're going to get 2 copies of the pentagon. One is going to be a child of group 1, one is going to be a child of group 2. So if I do that and I print out the hierarchy, we see that this is where group 2's origin is, and that there's a pentagon child here as well. And if we look through here, we see that this is group 2, and it has a pentagon child here, which has 5 points. And then group 1 also has the same pentagon child. And we know it's the same child because basically, the addresses match up. So this is called instancing, where you can take one geometry and place it in multiple places in a hierarchy. So for example, if you have a car again, you may only need to model one tire, and you can place that tire in four places in the car as part of 4 different hierarchies, and use the same geometry model for every tire and not have to model 4 different tires, which you shouldn't have to. It also saves on memory and so on because you only have one copy of the tire in memory. And here we have only one copy of the pentagon. There's only one pentagon. It's the pentagon with this address. It just happens to be placed in 2 places in the hierarchy. So when the draw method traverses the hierarchy to do all the drawing, it encounters it twice and therefore draws it twice. And each time it's at the right transform position based on the transformation of its parents. So if I take that pentagon now and I start translating it in Y, so it should move upwards in its local coordinate system, we can see that they both move, and they move in different directions, so they'll actually eventually collide or overlap, because this pentagon is moving along this green axis, which is its local Y coordinate, and this pentagon here is moving along this green axis. And then if I translate the pentagon, you can see that they both translate because there is only one pentagon. And so if I operate on it, both instances that are being drawn get the operation. All right, I hope that's not too confusing. I could probably have all kinds of charts and graphs showing tree structures and things like that, but I'll leave that as an exercise to the reader. So let's get a little bit fancier and make ourselves a robot arm. So we define a bunch of shapes: circles, pentagons, a square, a couple of squares, more circles. And these are just shapes, global variables. And what we then do is we start making groups, and we nest things into groups. So we have a group that is called wrist, and it contains the wrist shape and the hand shape. And then a group that is called elbow, that contains the elbow shape, lower arm shape, and the wrist group. And so on for shoulder and torso and waist. So waist is our top level group. It contains the waist shape, the torso shape, and the shoulder group. So let's actually, let's evaluate this, and let's actually print the hierarchy of waist. So here we have the hierarchy that we've defined. So you can see that, which shapes are which shapes. Perhaps the 16 ones are circles and the 4 ones are squares and so on, but it's not super illustrative because we don't know which group is which group, because we haven't given groups names or anything in their prints. But it's just to give you an idea that we have this hierarchy now. Oops. Click, click. All right. Now, let's add our waist, which is our root node of our hierarchy tree, to the scene. And then let's position all these things according to certain translates and scales and so on. So we're going to evaluate this whole thing here. And we have our little robot arm. So this is the waist, this circle. This is the torso, the shoulder, the upper arm, the elbow, the lower arm, the wrist, and the hand. Excuse the programmer art. So now, let's use our do hierarchy, and starting at the waist, and turn on all the axes. So you can see each shape has axes. And we can see that since we have scaled these squares, the axes have stretched as well because there has been a scale operation on them. So that's kind of a neat thing to notice, that the axes, since they're being modified by the transform in OpenGL, not just get rotated and translated, but also scaled. So now if I do certain operations, for example, let's take the shoulder and rotate it by -10 degrees. So you can see the shoulder here rotates, and all of its children and subgroups rotate with it. Let's rotate the elbow by +10 degrees. You can see it rotating and taking the forearm and wrist and hand with it. And then we rotate the wrist by 10 degrees. It rotates. And then if I take the waist, which is the root of the entire tree hierarchy, and rotate that by -10 degrees, everything rotates. So then I can define some functions that operate on this to let us do higher level things. So I mean, we're just rotating individual angles right now, but for example, let's define a function called reset pose that sets all the rotations back to 0. So if we define that function and then we call it, everything goes back to 0. So if I rotate things again, I can then reset the pose and everything goes back to 0. And then we can get fancier as a final thing in this lesson, which is basically we can define poses. So if I define a function called flex and it rotates the waist by -1, the shoulder by -5, the elbow by 15, the wrist by 10, and I execute that. Oh. Oh, I'm sorry, I got confused. I'm not executing it, I've defined a function. Pardon me, time for some more coffee, even if it is decaf. So that just defined the function flex. Here's where we actually call it and execute it. So each time I call the function, it incrementally does those rotations. And if you have some imagination, you can imagine a bodybuilder or a superhero or a robot flexing its muscles. And then we can, reset pose. We can define things in different ways. For example, if I want the waist to go the other way, I can make this go on +1, evaluate that. And you can see that the body rotates the other way. Or if I want the hand or the wrist to rotate the other way, I can reset the pose and say, let's have the wrist go in -10 degrees, so it's a different kind of flexing. And so on. All right, so that was a quick and brief introduction to groups and hierarchies, and we'll play some more with them in the next lesson. Thank you for listening, and goodbye.